Hello students, myself Dr. Jyoti C.K., Assistant Professor, Department of Physics, working in Government First Grade College for Women, Raichur. The title of the paper, Mechanics and Properties of Matter. So previous class we learnt about the law of conservation of energy. So today class is a continuation part where we are studying about the differential equation of the simple harmonic motion. When you say the particle is undergoing the simple harmonic motion, if the vibration of that particle is a periodically, that we say it is in a simple harmonic motion. So I have written here, if it vibrates periodically in a such a way that the acceleration of the particle is proportional to the displacement from the fixed point and it is always directed towards the fixed point, then particle is said to be the simple harmonic motion. 2 points we have to make a clear here. Vibration should be the periodically and acceleration is proportional to the displacement and it is always directed towards the fixed point. So then what do you mean by this restoring force here? The force which always bring back the body to the equilibrium position. That we call it as a restoring. I am repeating again here. A force always brings back the body to the equilibrium position. That we call it as a restoring force. So now consider the particle of the mass m performing the simple harmonic motion about its mean position. Here in this figure, O be the mean position at any instant. So let us consider now the particle be at a point P here, this one, which is separated by the distance of x from the O here. So then how we will write now? F is directly proportional to the x. So to remove this directly proportionality, you have to put some constant term. So therefore F is equal to minus S into x, where S is a proportional constant. And here the negative sign has been written here. The negative sign, what it indicates that the direction of the force and the displacement are opposite. So therefore the negative sign has been written now. So now write down the acceleration of the particle at a point P. What is an acceleration of the particle at the point P? As we know, the acceleration is nothing but here d square x by dt square here. Because from O to P, how much distance it has travelled? That is travelled a distance of x here. So therefore acceleration is nothing but d square x by dt square. So this gives the values of the acceleration of the particle at the point P, where at this point, at a point P. So now in the same way, how we will write the force here? Force will nothing but mass into acceleration. What is that acceleration? This is the acceleration and this is the mass. When you combine the mass with an acceleration, you will get the force here. So therefore, the force acting on the particle is m d square x by dt square. Now we got the value of the force here. So substitute here, the F is equal to S minus x. So now in the place of the force, substitute as a mass into the acceleration. So now it is written as m d square x by dt square is equal to minus S into x here. So again cross multiply here, d square x by dt square is nothing but S divided by m into x. In the place of S by m, substitute as an omega square, which is an angular velocity. So omega square is now S by m here. Substitute here. So this becomes now d square x by dt square is equal to minus omega square into x here. So now bring this term in this direction. So what you will write now? D square x by dt square plus omega square into x is equal to 0. So this you write it as an equation number 1. So this is the equation which we call it as a differential equation of the particle, which is executing the simple harmonic motion here. So some of the points we should try to remember while studying about the simple harmonic motion. About the acceleration. What is that first point? Make a point here. The acceleration of the particle which is performing the simple harmonic motion will be the maximum at the extreme position. This is the one we have to remember. The second one, when the particle occupies the mean position. Where is that mean position? That is at the point O here. I have shown here. This is at the mean position. So the acceleration is going to become a 0 here. When it is at the extreme position, the acceleration is a maximum. When it is at the mean position, the acceleration is a 0. And the third point is that acceleration is always directly proportional to the displacement. So these are the 3 points we have to remember here. So the equation number 1, repeating again here, the equation number 1 is known as a differential equation of the particle which is undergoing the simple harmonic motion. Simple harmonic motion of a light loaded spring here. So in this figure, let us consider the spiral spring here. The S be the spiral spring, whose one end is affixed to the rigid support and to the another end, that is the free end, where the mass is attached. So now here in an equilibrium of the spring, let the mass be at a point A here. So this will undergo the simple harmonic motion. When it will undergo the simple harmonic motion? When this spiral spring is pulled in the downward and it is released here. When this free end of the rod here, free end of the rod means this one. When this free end of the rod is pulled in the downward and it is released, so it will undergo the simple harmonic motion. In which direction? It will undergo the simple harmonic motion in a vertical direction here. So then when it is pulled in the downward direction, here the mass M will be at the position B here. Before it is at the A point. When it is pulled in the downward direction, the mass will occupy the position that is at the point B here. Then in between the A to B, how much the distance here? That is a Y be the distance here. So now let the tension per unit displacement of the spring be the K here. Okay. So then what you will write now? The force which is exerted by the spring, which is equal to K into Y here. Because you are applying the force in the downward direction, it is released, pulled it in the down and it is released. So it undergoes an oscillation, that is a simple harmonic motion in a vertical direction here, where the tension has been put at here per unit displacement of the spring, that is found to be the K here. So therefore the force, how we will write now? The force which is exerted by the spring will be now K into Y here. Now as per the Newton's second law of motion, how we will write the force? Force is nothing but mass into the acceleration. What is that mass? M is the mass and acceleration is d square y by dt square. Because from A to B, how much the distance it is? Y is the distance. So therefore we are written as dy square by dt square. In the previous, what we have written there? They have written as a dx square by dt square. That is a d square x by dt square we have written there. Why? Because from this to this, how much the distance it is there? It is an x here. So therefore we are written here d square x by dt square. But now we are writing as d square y by dt square, which is equal to minus k into y. Because this is the force. The force is nothing but m d square y by dt square is equal to minus k into y here. Again negative sign indicates that the force is directed in a upward. Because of that there is a negative sign here. Again bring this term in this direction. So that becomes now m d square y by dt square plus ky is equal to 0. So now dividing by the m here. So you will get now d square y by dt square plus, or else you cross multiply here. This you bring it in the cross multiply, or it divided by the m, or just you bring it the cross multiply here. So what will get now? D square y by dt square plus k by m y is equal to 0 here. Now compare this equation with the simple harmonic equation. That is equation number 1. This one. This you are comparing. This here. So now what we will write now? D square y by dt square plus, here in place of k by m you substitute as an omega square, y is equal to 0 here. So now omega square is nothing but k by m, or else omega is equal to square root of k by m here. But we know the time period t is equal to 2 pi by omega. Now what is the value of the omega? Omega is nothing but square root of k by m. Substitute this value here in this place. So what you will get now? Time t period t is equal to 2 pi square root of m by k. So this is the equation number 2 here. Just by knowing the value of the m and the k, we can calculate the time period. Now the determination of the k value. To calculate the value of the k, let us consider small m be the mass, which is a small mass attached to the free end of the spring here. So that small x be the increase in the extension of the spring here. Then k will becomes now m into g divided by x. Now substitute the value of the k in equation number 2. Where? Here. This you are going to substitute the value of the k here. So what you will get now? T is equal to 2 pi square root of m into x divided by small m into the g here. Where mg divided by x is a constant for the spring. So this is how we found the differential equation in the case of the spiral spring here. So next class we continue with the another topic. Okay.